Good morning. My name's Henry. Thank you very much for attending. I appreciate your time and your attendance. Today, indeed, I'm going to be talking about vector addition systems with states, and this is joint work with my two wonderful co-authors, Filip Mazowiecki and Coverability. I'm going to start, because I understand that some people in the audience are probably not vast experts, with a very warm toy example just to get started. But for those familiar, I think the title is rather explicit. I'm going to talk about the complexity of coverability in the case where you've got two dimensions, one of which is encoded in unary and one of which is encoded in binary. So I'll begin with a fun little example. So suppose you're planning a road trip, right, and you've hired a lovely red London Routemaster bus. And you've convinced 4 friends to join you on the start of your road trip, and you've got €100 collected together. And I hope you agree with me that a fun road trip really requires at least one friend. Being lonely is not very fun. And you really need positive money in order to continue running your bus. So here's the world ahead of you. You've got to traverse in order to get to the mountains, and you're trying to get to the mountains with a target of at least 5 friends to celebrate with you, and maybe €10. Doing so means you can buy some beer when you get there, I don't know. And so we begin. The first thing you do is immediately fuel up, and that costs you a lot of money, but that's fine. You still have non-negative money. That costs you €60 and you're left with 40. You continue forwards and you find a hitchhiker. And when you find this hitchhiker, you now have 5 friends. Fantastic. And now you're entering this southern sort of spooky forest, so to say, and you'll be losing friends at a rather alarming rate. And when you go through the forest, however, you find a lovely river full of large fish. The fish will fetch €20 at a market later on. Very valuable. But your friends get bored. When you fish, it's not favoured very well. So they'll leave. But you're too tempted. You fish once. And now you've got €60, which is fantastic, and you have 3 friends. Okay, maybe that's enough fishing, let's continue forward. And as you go towards the cafe, you lose a couple of friends. By the time you get there, you only have 1 friend left, but according to the official definition of a fun road trip, this is just about okay. And you've got €60, which is fantastic. And at the cafe, you've got a fantastic opportunity to buy some coffees for some people. Tell them about your road trip and convince them to join. Let's say you do this 4 times. Fantastic. Now you're back up to 5 friends. And you've got €40. That's enough to pay the extortionate toll road fee and get to the mountains. Now you've got 5 friends there, and you've got €15. You can buy a lunch or a beer or something and celebrate. And we've succeeded the target. But just take a moment to think. I fished once, and that was really important. If I fished twice, I would have run out of friends before I got to the cafe, and I wouldn't have been able to complete my fun road trip. And if I didn't fish at all, I wouldn't have had enough money that once I got to the cafe, I couldn't have recruited more people to join my road trip. So really, I'm just a good trick planner, and this is actually quite tricky. This is really a toy model or a toy example for the model I care about. So I'm going to talk about coverability, which is the problem we've just thought about in a 2-VASS with 1 unary counter. So the input to the problem, you're given a vector addition system with states, a VASS for short. In the previous example, the states were like the places, the transitions were like the roads, and the amount of money you lost or gained and the amount of friends that joined you or left were like the updates on the counters. And you also give an initial configuration and a target configuration. The target configuration QV, for example, is a state Q and a sequence of integers denoted by a vector V that tell you like what you're aiming for. In the previous example, I said I wanted at least 5 on the first component and at least 10 on the second. And the question is, from the initial configuration, can you reach some configuration with at least the values of the target? Like you could get there with more money and more friends and you're no less happy. And when I say run, I want to be really explicit. You must, when stepping through, always remain non-negative. Like in the previous model, or like in the previous example, sorry, when you've got at least 1 friend and at least 0 money. So you must remain non-negative throughout, otherwise you enter some illegal configuration. This is not very good. And the specific features of this model is that I have 2 components. One is in unary and one is in binary. In full generality, you can have more components, that's fine, but I'm really studying the case where you've got one encoded in unary and one encoded in binary. And to make it clear, if I say unary encoding, for the sake of intuition, think about updates of the form plus, minus 1, or 0, kind of like how friends can only enter and leave your bus one at a time. And for intuition, again, think for binary encoding, you can increment or decrement by any large number, like plus 60 or minus 20. And a very subtle technical point that I won't talk about too much, I might touch on at the end of the presentation. I actually allow both initial values and both target values to be encoded in binary. in context of the toy example, that's like asking for a really large number of friends to be on your bus when you begin, which is I allow for. It's a slight strengthening, but only a mild one, and never mind, I may touch on this at the end. Okay, so let me give some background, the complexity of coverability. So it's been long known that the problem in full generality is X space complete. That's when the number of counters is variable. You can have any number you like, it's just formed as part of the input. This was shown by an exponential space lower bound from Lipton in 76, shortly followed by an exponential space upper bound by Rakoff in 78. But if you fix the number of components, things become a lot simpler. So I'm going to fill up this table, and it's going to tell you the complexity of coverability with a certain number of components. And it turns out that the encoding really matters when you have a fixed number of components. Notice there was nothing to do with encoding in the top theorem. I could have given you any number of unary or any number of binary, and the problem is X space complete. That's because the lower bound holds for when unary encoding is allowed. So, okay, what about fixed dimension? So, if I have no counters, this is just deciding whether there exists a path in an undirected graph. The problem is, well, very long known to be NL complete. And it turns out that if I give you any fixed number of unary counters, the problem remains in NL, which is fine. This has been known for a long time. It turns out that Rakoff's upper bound is what gets you this. And so if you ask for exactly 8 unary components, this problem is still in NL. As for binary counters, if I give you 2 binary counters, this problem has been shown to be p-space-hard, might be rather surprising on first glance. And Rakoff's upper bound is able to show that if you're given any number of fixed any fixed number of counters, all of which are encoded in binary, then the p-space upper bound holds. And so this problem is p-space complete. So in particular, you could ask for 7 binary counters and 5 unary counters. This problem still remains in p-space because that's no harder than asking for coverability when you've got 12 binary counters, and that's in p-space. So then the only interesting case that remains is when you've got exactly 1 binary counter. That's the middle row of this table. So somewhat recently, a very sharp upper bound appeared for when you just have 1 binary counter. They showed it's in NC2. I wouldn't worry too much about this. It's been long known that this problem is in P when you have just 1 binary counter. The sharp upper bound is just something quite modern. We then studied the next most natural open problem, which is when you have 1 binary counter and 1 unary counter, and as the title may have suggested, that we show that this is in NP. And there are some fun problems that lay ahead with 1 binary counter and at least 2 unary counters. I might touch on these later, but don't worry about that for now. There is a fun section for the row of this table. Okay, I'm going to very quickly motivate and talk about related problems, but I'm going to flash through this. So VASS can be used to modestly model concurrent systems. You can convert a Petri net into VASS. I'm sure most of you are more familiar with this than I am. And then coverability can be used to query safety conditions or lack thereof in some systems. You might think for a moment that if I convert directly from a Petri net, the number of places corresponds with the dimensions. And so why one would study exactly 2 components? Well, it turns out that it's useful to study low-dimension systems to get an understanding for general systems. And already, coverability in binary 2-VASS is p-space-hard. So it makes sense to make some restrictions to understand what goes on beneath. And as for related models, there's this thing called 1p-VASS, which is when you have 1 counter and 1 stack. In this model, decidability is a famous open problem. We're not sure if it's decidable or not for the problem of reachability. That's a sort of restriction of coverability where instead of getting to at least the target configuration, you get to exactly the target configuration. Coverability in 1p-VASS is known to be decidable, however. It's p-space-hard, and I believe it's in X space, although I don't know if this is explicitly written in the literature. And then another related model, when counters are treated asymmetrically, are 2t-VASS. That's when you have 2 binary counters, and 1 counter can be tested for 0 whenever you like. It's a more powerful model. In this, both coverability and reachability have been shown to stay in p-space, making them p-space complete. Notice that if you were able to 0 test both counters, then you've got a 2-counter machine, and reachability and coverability in this model is undecidable. So we're really playing with fire. Okay, so I'm going to restate our contribution to make it as clear as possible. We showed that the coverability problem in 2-VASS when you have 1 binary counter and 1 unary counter is in NP. And to contextualize this, If you have two binary counters, the problem is p-space complete, and if you have just two unary counters, the problem is NL complete. This allows an exponential multiplicative space gap between the two problems, and so we studied the most natural intermediate, which is when you have one binary and one unary. And we show indeed that the complexity lies somewhere between the two, NP in fact. Okay, so if you were to show this, what would you do? Common approaches in the area are to show that small witnesses exist for instances of coverability, and we're no different, but we have to spend a lot of effort on our small witness type. We have to sort of invent something slightly new. So let me speak about a common approach first. You'll see in the literature many times the phrase linear path scheme and an expression of this form pop up. A linear path scheme is a collection of paths connected to cycles connected to paths connected to cycles. You can think of the taus as paths and the gammas as cycles. And this asterisk on each cycle says I take the cycle some number of times. And so really this represents a family of paths. If you instantiate how many times you take each cycle, you get a new path. And the goal would be to show that coverability is witnessed by paths of this form. So I'm going to really precisely speak about one path, which I'm going to call a linear form path. So I'm going to instantiate exactly how many times I take each cycle. So these exponents E1 through EK say I take the first cycle E1 times, I take the kth cycle EK times. And just to stress that the paths tau I connect between two cycles, gamma I and gamma I plus 1. What's the point, right? What is the point? So if I have a witness of, say, coverability written in linear form, then I should gain some succinctness. If you were to write out an entire path or an entire run, you would write this as a sequence of transitions, transition by transition by transition. This is pretty inefficient. If you take a certain cycle a large number of times, you could save yourself some memory by just writing down that cycle once, and then writing down in binary how many times you do this. Imagine you take a cycle consisting of 10 transitions 500 times. That's 5,000 transitions, that's ridiculous. But instead you could write down just the 5 transitions and then the number of times you take this cycle. And you do so in binary and you save a lot of space. To sort of motivate why, I'm just going to talk about coverability in 1-VASS to kind of get warmed up. So I claim that coverability in 1-VASS is witnessed by polynomial size, linear form paths. There's only 2 cases to consider. The first is if you have a short path from the start to the target. And if you have a short path, that's fine, you can just write it down. Otherwise, you must take a cycle. If you take a cycle, there are 2 cases. Suppose you take a negative cycle. For coverability, it's a terrible idea. If you did not take the negative cycle, you would have a greater counter value, which you're better prepared for the rest of your run. So you never need to take negative cycles. Instead, you might take a positive cycle, which is fantastic. If you take a positive cycle, you can take this as much as you like, raise your counter to some arbitrarily large value, and then you're fine to go to the target. Indeed, this is the kind of picture that you would expect. You either have a short path, or otherwise you have a short path to a short cycle to a short path. And I can then write these down in linear form. Obviously, I can write the short path down explicitly, that's fine. And if I have a short cycle, then I can write down the path, the cycle, how many times I take the cycle in binary, and then a short path. And so, very informally, I think that it's clear that 1-VASS, the coverability in 1-VASS is witnessed by polynomial size linear form paths. I'm now going to spend some time on an example that kind of motivates that this previous common approach for simple linear form paths is perhaps not enough. This example is quite tricky, but I think it's pretty eye-opening. So I'm going to ask for an instance of coverability. I'm going to start on the left state. I'm going to start there with 0 on both counters. And I want you to solve an instance of coverability where you're aiming to get state Q on the right-hand side. I would like at least 20 on the first component, and I would like at least 10 on the second component. So you can see you're probably going to have to use these cycles. It's set up in such a way that this is necessary. The bottom cycle, notice it subtracts 29 and adds 5 on the first component. So it's quite negative on the first component. The top cycle is a bit more positive. It gives you 25 on the first component, but it takes away from the second component. So you're going to have to very carefully juggle these cycles. So I'm going to take you through how one might witness coverability here. So first I should really stress, just to really hammer it home. When I say run, I really want every configuration, piece by piece, to have non-negative components throughout. So first, I think it's a good idea to take this bottom path from the start. So I'm going to take this green path row. I'm going to enter a configuration. I'm just going to very casually name the middle node C. It's not drawn on the picture, but just pretend a C is there. And I'll have 10 on the first component, and I'll have 2 on the second. And from here, I can afford the top cycle, because I've got 2 on the second component. I can survive the first 2 transitions. I'll just have enough on the second component to get by it, and I'll come back to the node C. But I can't afford the bottom, because I don't have 29 counter on the first, so I'd be killed off if I took the bottom cycle. So, okay, fine, I'm forced. I'll take the top cycle, which I call alpha. Now from alpha, once I've taken this, I get to a configuration where I've got 35 on the first component and 1 on the second. So yeah, I increase the first component at the cost of decreasing the second a little bit. But now I can afford the bottom cycle. So now I have more than 29 counts, so I can afford the bottom cycle. I'll call this beta. Notice that if I take the cycles in sequence, I gain 1 on the first component only and 0 on the second. So I'm now able to take these cycles in alternation, alpha, beta, alpha, beta, alpha, beta. I can do this as many times as I like, and I'll get the first counter's value as large as I like. And notice I'm looking to cover 20 on the first and 10 on the second. And by alternating, I don't touch the second component. So at some point I need to increase the second component, because this last transition that will get me to state Q is very negative on the first component, and it subtracts 1 from the second component. The only way to gain value on the second component is by taking the bottom cycle. You see, I get +1 on the second component by taking the bottom cycle. But doing this is expensive. I have to spend a lot on the first. It takes 24 away, and I want to maybe take this bottom cycle something like 24. I need to subtract 24, so I'm going to have at least 240 counter on the first to even afford 10 iterations of the bottom cycle. So I'll pluck the rabbit out of the hat. I'm going to take it 350 times. I have to alternate alpha, beta, alpha, beta, alpha, beta 350 times. And into this configuration with 360 on the first component and just 2 on the second. That allows me to take 10 iterations of the bottom cycle. I then enter a configuration with 120 on the first component and 12 on the second. And now I can fire this last transition. So I can fire this transition, I subtract 100 from the first, I'm left with 20, and I subtract 1 from the second, and I'm left with 11. And look, I just made coverability. So I ended up in a configuration with at least the first component and at least the second component. I just survived, but it took a lot of effort, and it's a very complicated path. I had to alternate cycles, and it's kind of difficult. I've kind of expressed it in an easy to understand format, and I hope you enjoyed my explanation through this example. So linear form paths aren't enough. We introduce a new small witness type, which I'm going to call compressed linear forms. They look the same, right? So you have to pay attention, unfortunately. I'm going to have paths row to cycle sigma, and I'm going to take each cycle a certain number of times. But the catch is that each path and each cycle themselves are represented in linear form, hence compressed linear form. Why should I care about this? The size is measured similarly. I measure the size of I measure the size of compressed linear form path as the sizes of the linear form paths and the size of the linear form cycles, and in binary, the number of times I take each cycle. What's the gain? I gain succinctness. Suppose I have a sequence tau gamma 1, I take E1 times tau 1. And suppose that itself is a cycle that I take many, many times. If I was to write this out, look, it's a really long linear form where I have loads of paths and loads of cycles back to back to back. It would take me a lot to write this all down. My succinctness gain would be writing this down and saying I do it F many times. And so then this expression is very small. I just have to write down how large tau naught is, gamma 1, tau 1, and I just have to write down E1 because it's fixed. That's why I fixed it, and I have to write down F. And this example demonstrates why one would care about a compressed linear form path. So I've kind of written out the run that we took previously, and notice that the first part can be thought of as a small linear form path. The middle part itself is a linear form cycle, right? I can write this down as 2 consecutive cycles that I take a large number of times, and then the final bit itself is a small linear form path because it's a cycle I take some number of times followed by a simple path. For the technical contribution, it is roughly what you would expect by this point, which is that instances of coverability in 2-VASS with 1 unary counter are indeed witnessed by compressed linear form paths. I wouldn't have told you about them for no reason. And indeed, these paths are compressed, are of polynomial size. We get to this through two techniques, which I would love to talk about, but I don't have enough time in this presentation, so I implore you to come and find me and talk to me about them if you're interested. What could happen? Like, what's the worst thing that could happen? Well, the worst thing that could happen is that the witness that you have is a long sequence of short paths and short cycles. And you just don't have enough space to write this down, right? That's imagining your path is like a really large number k. That's like horrendous. So the first thing is I observed that you only need a polynomial number of distinct short cycles that you need to consider for coverability. So you can replace your large number of potentially exponentially many distinct cycles with a polynomial number of distinct many cycles. They may occur exponentially many times, I'll handle that in just a moment. But at least we dealt with something. And I'll note that if you would like to steal these techniques, that's fine. You require a coverability objective here. So this does not work for reachability, and so I'm making it clear like how these techniques are applicable. And I really can't do this with more than one binary component. If I have more than one binary component, then I'm not in a good place. But this works if I have 2 or 3 unary components though. And the second technique is, once I've got potentially a long linear form with lots of cycles, but only a polynomially many distinct ones, what I'm going to try to do is group them together. If I've got 2 cycles that are the same, that are kind of far apart in a linear form, if somehow I can bring them together, then I can gain succinctness by writing them together and saying I take them 2 or 3 or 4 times. And so I reshuffle short paths and short cycles, hopefully collecting them together. And one of 2 things can happen. Either I succeed and I get a small linear form path and I've got a small witness and I'm happy, or I fail. Maybe I failed for some combinatorial reasons. And in this case, I will find a cycle that is pumpable. Like in the example we saw, there was a combination of taking alpha then beta that gave you +1 on the first component and 0 on the second. And I could like shoot this up. And in effect, I can simplify the problem to only have one component. And I claim that that will always happen if you don't find a small witness. And then that will be the basis of a different kind of small witness. Here the requirements are that this does not work for more than 2 dimensions as far as I'm aware. And at least one of them needs to be unary. If they're both binary, this doesn't work. So really, the 2 techniques together they're kind of baked for this problem of coverability with one binary counter and one unary counter. But individually, this second technique could be used for reachability. So they have some potentially wide applications. Okay, I think I'm close to needing to conclude. So just to sort of reiterate, to sort of summarize, I claim that coverability in 2-VASS with one unary counter and one binary counter is an MP, and I just gave you the technical contribution that does all the back work and improve it, obviously. The idea is just to guess and check a compressed linear form path of polynomial size. You might be curious on how one would check this. This works just like checking a linear form path. You don't need to check whether every iteration of every cycle is valid. You just check if you can do the first one, and if you can do the first one, you try and do all of them at once. If you can do all of them at once, then you succeed. And so you can process a linear form path by going path, then first iteration of a cycle, then all iterations of a cycle, and then you move on like this. And this works too for compressed linear form paths. And there are some interesting open problems here. So firstly, we don't have a matching lower bound, unfortunately. So we haven't been able to show yet that coverability in 2-VASS with one unary counter is NP-hard. We do, however, have NP-hardness when you have 3 unary components. So you have 1 binary and 3 unary counters, we get NP-hardness. Restricting this down by shaving off the number of unary components seems really difficult. I think this is a really hard problem, but a very interesting one nonetheless. And so when I said earlier on that table with the ... remaining, there are some problems out in the distance where we have some lower bounds. And I talked about on the definition slide that the encoding of the initial and target configurations is important. I really think this is a source of hardness. I think that if you have binary encoding on the source and target, I think you can get hardness. But without it, it seems really tricky. So I think these subtle differences make a large difference when you start to ask about lower bounds. And another open problem is, what about reachability? I said that my techniques end up combining so that you're forced into using the coverability problem. Is reachability in 2-VASS with one unary counter and one binary counter in NP? It's a good question. We have, unfortunately, a demotivating example. So I can present you, if you're interested, with an example of just 2 states and 4 transitions, and an instance of reachability that only has one path that witnesses it, and that path is disgusting in a sense. It is not compressible in any meaningful way that I can understand. It's certainly not compressible to a compressed linear form path, and so one would have to get very creative and find a new form of small witness type if they hope to show that indeed reachability in 2-VASS with one unary counter and one binary counter is in NP. I'll note that this problem is known to be NP-hard already, because if you have just one binary component, the problem is NP-hard. And so the question is, if I add a unary counter, can I keep it in NP? I think that the second problem is really difficult, so I'm not so sure. Okay, I think that's everything. Thank you very much for your attention. I hope there's time for questions. Thank you very much.